My name is Simon Tarbush, and today I'm going to present our recent work on cross-field channel estimation for ultramassive MIMO terahertz system. This work has been accepted for publication in IEEE Transaction on Wireless Communication. This work is done by me, Simon Tarbush, in collaboration with Dr. Anom Ali, with Samsung Research America, USA, and Prof. Tariq Al-Nafouri with Information Science Lab at King Abdullah University of Science and Technology, KAUST, Saudi Arabia. This work is supported by KAUST Office of Sponsored Research, and please reach out by email to us for any questions regarding this paper. Let us start by some motivation for high-frequency bands and ultramassive MIMO arrays. As we all know, the use of high-frequency, large bandwidth, and ultramassive multiple input, multiple output system is likely in the next generation wireless networks. For example, the terahertz band is a promising enabler that can satisfy the extreme throughput requirement of up to terabits per second. Recent channel measurements for terahertz channel showed that the propagation in some scenarios is dominated by the line of sight component. Moreover, the number of channel paths is typically limited with high gain massive arrays. Therefore, the terahertz channels are extremely sparse, which encourage using complex sensing strategies for channel estimation. However, the achievable communication distance is limited due to the high frequency space path loss. Thus, ultramassive MIMO antenna arrays at the transmitter and receiver are necessary to get high beamforming and combining gains and achieve longer communication distance. To this end, the use of short wavelength, large arrays, and limited communication distance imply that the far-field assumption cannot be always made, and the near-field communication will occupy a significant part of actual terahertz coverage. For example, by taking the MIMO-Rayleigh distance as a boundary between the near field and the far field, we can note the following. This distance is proportional to the square of the summation of the transmitter and the receiver array aperture and is inversely proportional to the signal wavelength. So, by doing some calculations for specific DT and DR versus the frequency, we can note like at this frequency, a significant part of the actual terahertz coverage will be in the near field. Let us now define the cross-field problem that we are focused on in this work. So, as we mentioned, the far-field assumptions break down for high-frequency, ultramassive MIMO system. There has been considerable interest in near-field communication over the last few years. However, in practice, a mobile user will be moved back and forth between the near field and the far field regions of a system. This gives rise to a cross-field communication problem where first it needs to be determined whether the user is in the near or far field, and subsequently some appropriate action needs to be taken. Particularly, channel estimation strategies have been developed for near field and far field, but to use the most fitting strategy at any given time or location, first it needs to be determined whether the user is in the near field or the far field. In our paper, we adopt the following architecture at the transmitter and the receiver. Let's dive into it. Actually, many novel candidates architecture suitable for high-frequency band and adopting hybrid beamforming have been proposed in the literature. One promising array architecture is the array of subarray. In this architecture, the TX and the RX ultramassive MIMO array are divided into subarrays, where each subarray contains many array elements, and each subarray is connected to one radio frequency RF chain exclusively. This provides several advantages. Example, reduced complexity and power consumption, and also makes channel estimation simpler, as we showed in our previous work and as we will see in this work. Now, regarding the channel modeling for ultramassive MIMO array of subarray terahertz system, we all know that the spherical wave model, for short SWM, is the ground truth model for all distances and is also used in the near field region. This model captures the magnitude and the phase variation between the array elements so that the channel model is accurately modeling this variation. Let us take in our example, in our system, and suppose the TX contains QT subarrays, and every subarray is composed of Q bar T tightly packed antenna elements, and the same assumptions are applied for the receiver. Then the spherical wave model MIMO channel between the QR RX subarray and the QT TX subarray at subcarrier K can be written. So, by deeply looking into the channel equation, we can note the following. The 3D distance, the angle of arrival, and the angle of departure vary across the array element. It is worth mentioning that the array steering vector for the near field region is a function of both the angle and the distance. Now, to sum up with this, although SWM is accurate for channel modeling, it makes channel estimation more complex. On the other hand, when the communication distance between the transmitter and the receiver is much larger than the antenna array, so we fall in the far field region, the planar wave model, for short PWM, can be utilized as a sufficient approximation for the SWM. PWM is a simple model, but still with a high accuracy in the far field region. The PWM only describes the phase variations across the array element. The channel in this field only differ in phase, and this phase depends on the angle and inter-element spacing. So, what's the meaning of planar wave model now for an array of subarray? For this architecture, the planar wave model implies that the propagation model across all the subarray is the same, which means like the 3D distance, angle of arrival, and angle of departure are not varying. And we can, like, for example, take one reference subarray. For example, we take the first reference subarray at the transmitter and the first subarray at the receiver, and we model the channel based on this. And then the whole array of subarray will have a similar model. This is the planar wave model. However, for the array of subarray, this provides for us another opportunity, which is a third model that can describe the channel, which we call through this paper hybrid spherical planar wave model, for short HSPWM. The HSPWM captures only the phase difference across the nearby array element, but capture both the phase and magnitude variation across more separated array elements. So HSPWM is particularly suitable for an array of subarray architecture, where the elements within a subarray can be considered nearby array element, whereas elements across the subarray can be considered more separated. Moreover, we know, like in an ultramassive MIMO system, a subarray usually contains substantially fewer array elements than the whole array. Thus, based on the HSPWM model, a planar wave model is used within the subarray, and a spherical wave model is used across the subarrays. Thus, we can see like this model provides a good trade-off in modeling accuracy and complexity. In this paper, we introduce the term called intermediate field to be the region where HSPWM accurately approximates SWM, but PWM does not. And the HSPWM is suitable for the intermediate field. Now, Let's look a little bit in the channel model. We can note like that the 3D distance, the angle of arrival, and the angle of departure are varying across the subarrays. Okay, to wrap up on the channel modeling, we demonstrated now that there are 3 field regions, and within each region, there is a suitable channel model to be used. Now, let us move to discuss the channel estimation by following the previous models. As we previously mentioned, the terahertz channel exhibits a sparse nature. So we can apply compressed sensing-based channel estimation algorithm. Usually, this algorithm perform a greedy search over a set of sparsifying dictionaries. And these dictionaries differ across the region. And the overall complexity of the used solution will depend on the size of the dictionary. For example, in the farfield, we can use the angular domain dictionary, which is, as we can see here, uniformly sample the angle grid. However, in the farfield, we cannot utilize such dictionary. We should utilize another dictionary since the steering vector is a function of both the angle and the distance. One of the used dictionary is the polar domain dictionary, which is a two-dimensional dictionary that uniformly sample the angle and non-uniformly sample the distance. Hence, based on this, we can note the following. If we apply the near-field channel estimation, this will be the accurate one for all regions, but they are complex, of course, due to the use of two-dimensional polar domain dictionary. Moreover, near-field channel estimation algorithm can be applied to the far-field. However, they show unnecessary complexity since the PWM-based channel model is sufficient. On the other hand, if we perform far-field channel estimation in the near field, it will be suboptimal. Adding to this, typically, the user moves between the field region, then using a suitable method for a specific location helps reduce the computational complexity. And now the question is about the optimal selection of channel estimation method to minimize the complexity while retaining the performance of the channel estimation based on the most complex and accurate model. This is the cross-field channel estimation problem. So, which entails the following 2 steps: determining whether the user is currently in the near, intermediate, or far field, using the appropriate channel model and estimation method accordingly. So now let us move to our proposed strategy for solving the cross-field channel estimation problem. First, we need, as we mentioned, like to solve this problem, and then, which means like let us define and select which is the suitable strategy for estimation, and after that, we will go and start enhancing the estimation performance by benefiting from the structure of the array of subarray. So we aim to answer the following question: can we determine the appropriate channel estimation method based on the received signal even before initiating the estimation process? The second question, can we exploit the geometric structure among subarrays to enhance the compressed sensing-based estimation by using the prior information? So let us go to the first part of our proposal, which we called appropriate channel model selection. What is the aim here? We seek a rough estimate of relative distance or an indicator for which model, SWM, HSPWM, or PWM, should be used for channel estimation before starting this procedure. Consequently, we introduce a metric we called model selection metric that when it is compared to a predetermined offline threshold can provide the information on which channel estimation strategy to be used. So we will have in this section 2 parts, the proposed metric and the threshold. Let us now discuss the intuitive behind the model selection metric we call through this paper as ETA. The basic idea is to analyze the variation of received pilot signal across the subarray. We think like we will have significant variation for this receives the difference across the received signals between the subarray and the near field, and some variation in the intermediate field, while we expect slight, if any, variation in the far field. So let us pick up like this figure and try to understand the meaning. This is a transmitter subarray. So let's say we only select the first subarray, and this subarray start to transmit the first beam pilot, the beam forming vector. At the receiver side, we let all the Rx subarray utilize the same random beamformer weight. Let's take the case of the first Rx measurement. In the near field, the reference subarray has high power than the last subarray, resulting in a large difference between the received power of the two. While in the far field, however, the angle of arrival becomes comparable on all subarrays, and the array gain in the direction of angle of arrival is also comparable, giving a small value of the proposed metric. For example, let's take another one, which is the last measurement. The reference subarray has a small gain, but the last subarray has a large gain, keeping the difference in power of these two subarrays large. However, in the far field, the difference remains small. Now, by considering all the possible Tx and Rx measurements, we can utilize these measurements and the idea of capturing the power of the difference of received signal for all Rx subarray pairs to get this information. So we will expect that the model selection metric exhibit a decreasing trend with distance. It's also worth to mention that the reference Tx subarray is sufficient to determine which estimation method should be used. Now, let's go to the second part of the channel model selection, which is determining the offline thresholds, which are used to as a demarcation of different regions. The idea here is like we need to compare the model selection metric to pre-compute threshold, which represents the region boundary. So to determine this offline threshold, we do some kind of training. We define like a vector of distances that range from near field to far field. Now, for each distance, we will generate the accurate channel, which is the channel based on the spherical wave model. And we start the training over multiple rotations and trials. Now, we collect all the metric value for every communication distance, and we plot the CDF of these signals to get finally the threshold, which are gamma SH and gamma HP. The threshold gamma SH is used to distinguish between near and intermediate fields, whereas gamma HP is used to distinguish between intermediate and far field. The process of learning ETA is simple, and hence we don't require complex solutions. This is an advantage of our solution. Now, those pre-computed thresholds will be used later in the online operation. Now, let us move to the second part of our proposal. To this point, like we finished solving the cross-field problem, and we aim to answer the second question, which is after selecting the suitable channel model for each model, now we know which channel estimation strategy we can use. So now we are thinking about how we can enhance the performance further by leveraging the structure of the array of subarray. As we know, the conventional array of subarray estimation entails solving the compressed sensing problem for all TX-RX subarray pairs separately by using a suitable algorithm and dictionary. For example, in the near field, we can use the polar dictionary, and for the far field, we can use the DFT angular dictionary. However, the greedy search of the compressed sensing algorithm depends on the size of the dictionary. Then, the naive procedure of estimating the subarrays can be enhanced by incorporating some prior information into the channel estimation algorithm. Our idea is based on the following. Like, we know that if we take the previous subarray estimation, this can be used because we know, like, between the subarrays there is some geometric relation. So if we take that estimation of the reference subarray and use it as a prior information to estimate the subsequent subarray, this will result into reducing the search space. So instead of searching over the whole space, we will go and search over selected number of beams. These beams can be different or represent different things between polar and DFT dictionary. For example, it can refer to angle and distances beam for the polar. What is the reduced dictionary method? It's depending on, like, we get the estimation from the first subarray, and we select the columns that representing that channel. Now, we construct an oversampled dictionary. We do a correlation between the previously estimated subarray and this oversampled dictionary, and we select number of columns that have the largest value. Note that the number of selected columns will be always less than the original size of the dictionary to reduce the computational complexity. Then we will create a new dictionary called the reduced dictionaries. We expect that the resultant dictionary, when used with the algorithm, will result in two things. The first one is decreasing the computational complexity. As we mentioned, we use the number of columns to be less than the original dictionary size and to enhance the estimation accuracy. This can be interpreted as search space is reduced. Then the probability of detecting the correct support from the compressed sensing-based algorithm is increased. However, as we mentioned before, there are three types of field. So now let us talk into details how the reduced dictionary will be applied in the near field, far field, and intermediate field. We start by the near field with reduced dictionary. So in the near field, as we mentioned, like, the channel state information are different across different subarrays. And each, like, the beam is a function of an angle and distance. So, for example, the ground truth of the first Rx subarray can be here, and for the last Rx subarray can be here. Then, what we do for the first RxDX subarray channel, as we don't have any prior information, what we will do is we will perform the search over the whole space in the polar domain, which is, as we mentioned before, a dictionary that divide the angles and the distance. Now, as we mentioned, like, we get the initial estimation. Now we use this estimation in the subsequent subarray. Specifically, for the second subarray, we know that the best beam to be used for the second subarray should be around the first estimation. So we don't perform a search over the full dictionary. However, we use the reduced spaced dictionary and shrink the dictionary to some angles and distances candidate around this region. And the same applies for the other. Now, let us move to the far field reduced dictionary that is compatible with an array of subarray. As we previously explained, the planar wave model for the array of subarray means that the channels are the same across all the subarrays, which means, like, the reduced dictionary can be interpreted as the following. We do the channel estimation only for the first reference channel, and that's it. Even if it is over the complete search, we will not do any other search for any other subsequent subarrays. So the PWM, and we call this method as PWM-RD, has low computational complexity as it only does a channel estimation utilizing the far field dictionary only once. And also it has low pilot overhead since the pilots are only transmitted once from the TX subarray. Now, let us move and see the third case, which is the intermediate field with the reduced dictionary. For HSPWM, we use a similar strategy as the near field, a reduced dictionary, but we utilize the far field dictionary instead of the near field dictionary. Also, as we can see from here, like the best beam will be different across the subarray and refer to different beam. So we will do the same. We will start by searching the complete search for the reference sub TX RX subarray. After getting this initial estimate, we will use this information by utilizing the reduced dictionary algorithm to reduce the search region. Then the search space is narrowed down for the other RX subarray. Then now we have explained the two parts. Let us combine the proposed solution, and we called cross-field RD-based compressed sensing channel estimation. Here, what we will do, let us first discuss what compressed sensing we are using in this work. We are using the simultaneous OMP. So instead of solving the compressed sensing problem for each subcarrier, we can exploit the common support property and use a single compressed sensing problem to be solved across all the subcarriers by using simultaneous OMP. Now, the inputs for our algorithm are the following. First, the number of paths to be estimated, which we denote as L bar, which is different from the original L, which is the number of paths when we generate the channel. The second two inputs are the pre-computed offline thresholds and the sensing matrices, which are different for different regions. Now, we will start like sending the pilots from the reference TX subarray and receiving them across all the subarrays, RX subarrays. And we compute the value of the model selection metric, and we compare it with the pre-computed threshold. Now, based on this, we will decide, we have three cases. Either we are SWM-based channel estimation, HSPWM, or PWM. Like for the SWM-based and HSPWM-based, we will do the following. First, for the first TX subarray channel estimation, we use the conventional SOMP with the full space polar dictionary, while for the remaining RX estimation, we will use also the SOMP, but with the reduced dictionary. Now, for the second subarray, we will repeat the same operations here till finishing all the TX subarray. If the case was the detected or the selected channel estimation to be PWM based, hence here we only need to perform this estimation only once. Now, after completing this, we should mention like we need a feedback to the transmitter to let the transmitter know either to continue or stop the pilot transmission after the first step, which is sending the pilots from the reference subarray. After doing all of that, we should do some steps which are like selecting the analog beamformer, then finding the equivalent channel, and finding the baseband precordant to complete the hybrid beamforming. We use the following simulation parameters. For the channel generation, these generations are based on a modified version of our previously published simulator called TeraMIMO. The spherical wave channel model is always used for all channel generation as it is the most accurate model for all communication distance. And we simulated 2 terahertz scenario, where the main difference between those that the TX-RX ultramassive MIMO array have different apertures. So here I want to add one thing, like our simulator TeraMIMO codes are publicly available on GitHub. And also in our ICAS paper, we previously started the HSPWM-based estimation for the line of sight, and we showed like also the initial idea of the reduced dictionary, which that paper developed for the line of sight channel cases, is working with both OMP and SOMP. And also in that paper, we work with the UPA, not the same as here, we utilize a ULA. So you can also go and check the codes. Also, we make all of the simulation code for this work available, and you can easily access them on GitHub. Now, let us move to the results. First, we start by analyzing the proposed model selection method we refer to as ETA. As we can see from this figure, first we can note the following. The proposed metric exhibits a decreasing trend with distance, as we expected before. So the metric also, as we can see, can be work with line of sight and also in the presence of multipass. So the plots are for different number of channel passes and for different SNR values. First thing to note, like here in the near field region, we can note like there are a notable degree of variation in ETA. Moving to the intermediate field, can note like a sharp decrease in ETA. This drop is a result of some variation in the Rx power between the subarray as we transfer from the near field region to the intermediate field region. After that, in the third region, which is the PWM region or the far field region, we can note like the metric is almost constant. Also, so we can note the following, that the proposed model exhibits like different behavior across SNR level. So we can note two things. In the region with low Rx SNR, such here, like the received SNR is 0 dB, we can note like ETA shows minimal variation, indicating that it becomes challenging to favor one channel estimation method over another, as all methods are expected to result in low estimation accuracy under this condition. However, the proposed metric in scenarios like for moderate and high SNR level, for example, here for 6 dB and or more, we can see that the proposed metrics serve as an effective indicator for selecting the most suitable channel estimation method. Now, let us move to the evaluation of the proposed metric we called proposed crossfield RD in terms of NMSE, computational complexity, and achievable rate. We omit from this presentation the achievable rate results. Here, we can note in terms of NMSE, like in the near field and the intermediate field, or the majority of the intermediate field, we have gain in terms of NMSE over all of the reference methods. As well as we can note also that the computational complexity is less than all of the methods. Here in the near field region, we can note like the far field based array-of-subarray estimation have a slight less computational complexity compared to our proposal, but this is not a problem. Why? Because as we can see from here, like there is a huge performance loss when we apply that method. So it can reach like up to 4 to 5 dB. Then our proposed method can give like an advantages over all the communication distances. And at very high large distances, we can note like all the methods have almost the same performance. Now, to sum up in this presentation and this work, what we have done, we solved the crossfield channel estimation problem for the array-of-subarray based architecture for ultramassive MIMO terahertz system. We introduced a model selection metric to determine whether near, intermediate, or far-field channel estimation is appropriate. Finally, we proposed a reduced dictionary method to exploit the geometric relations between multiple subarrays and reduce the search space. And please feel free to reach us if you have any discussion about the codes or the paper.